All right, so let's look at an example circuit. So here, what I have is I have a current source and a voltage source, and I have a series of impedances. And let's say my goal is to find, in the end, V sub C of t. Okay, what is that equal to? So to approach that problem, the first thing we have to do is we're going to say we're going to use the Laplace impedance concept, which says that I need to transform this circuit over into the Laplace domain. So instead of saying In here, I'm going to write it as the transform of that, whatever that is, In of S. And I have a current source. And I have 1 over SC is the impedance of that capacitor. SL is the impedance of that inductor. And then the resistors are just simply R1 and R2. And then this voltage source here remains as Vn of S. Okay, so that's our complete circuit. And our goal now is to find V sub C of S. Okay, and if we wanted to find V sub C of t, we know that V sub C of t is related to V sub C of S through the Laplace transform. Okay, all right, so let's take this approach. Simplest thing to do is to look at this circuit and see that I want to use superposition. Okay, so I'm going to make use of superposition. So I'm going to do basically the superposition in 2 steps. So step 1 will be to, and for me, turn off Vn of t. All right, so basically turn off Vn, so set it equal to 0. So setting a voltage source equal to 0 makes it a short circuit. So that means that the circuit simplifies itself down to In of S. Here's the capacitor. All right, 1 over SC for that. I'm going to give this not V sub C of S, but I'm going to call it V sub C In. Okay, let's call it that. Here's the inductor. Now because the voltage source is off, I just have R1 in parallel with R2. All right, so if I look at that, the first thing I'm going to do for myself is to say, well, if I draw a line right here, basically I see I have a collection of impedances in parallel with the current source. So I see that I can simplify that circuit like so. I have 1 over SC here, V sub C In here, and then I got a parallel impedance combination that I'll just draw with a box right there. And inside this box would be SL in parallel with, SL in series with R1 in parallel with R2, like that. Okay. So what I can see is that the voltage across SL plus that series combination is the same as the voltage across the capacitor. And if I can't see that, I could do a KVL around this loop right here, and I would see that. Okay, so I can simply now say that V sub C In of S has to be equal to In of S times this parallel combination, 1 over SC in parallel with SL plus R1 in parallel with R2. Now, at the beginning of the problem, I did give numbers for these things here, but I'm not going to use those right now. All right, I want to actually simplify this guy in multiple steps. So first thing I want to do is just take this term right here and simplify it. Okay, so that would become, if I know anytime I have 2 things in parallel, R1 in parallel with R2, I know that that always simplifies to this expression Okay. More generally, it's 1 over R1 plus 1 over R2. If you simplify that, it becomes the expression above. So this guy here becomes SL plus R1 R2 over R1 plus R2, like that. Okay. So how do I approach this? So what I need to keep doing is I need to say, well, that's in parallel with 1 over SC. Okay. And remember, this is times In of S. So I need to simplify this whole expression now. Well, that's going to get ugly, right? What do I have? I have 1 over SC times SL plus R1 R2 over R1 plus R2. That's the top. So basically I'm trying to use this relationship here. So on the top I'm multiplying the two things, and on the bottom I'm adding them, right? I have 1 over SC plus SL plus R1 R2 over R1 plus R2, like so. Okay, so to approach this, what am I going to do? Well, basically what I'm going to try is I want to get my transfer functions always to be a function of S, a polynomial of S. So one thing I could do at this point if I wanted to is to plug in numbers. I'm not going to do that just yet. I'm just going to simplify this by multiplying the top and the bottom by SC times R1 plus R2. So in other words, I'm multiplying the whole expression by 1 when I do that. Okay, so that turns this into, so these SC's on top cancel, so this becomes SL R1 plus R2 plus R1 R2 over R1 plus R2, right? I multiplied this guy here by the first term, plus S squared LC times R1 plus R2 plus SC times R1 R2. Now if I go up to the top here and I plug in the numbers that I've got, this guy becomes simply 18S plus 45 divided by 18S squared plus 45S plus 18. Okay. All right. So that is the first transfer function. I guess what I should be clear is all right, this is times In of S, right? This here is just that expression. So I have BC In over In is equal to 18S plus 45 over 18S squared plus 45S plus 18. Okay, so that's half the problem. Okay, the other half of the problem is if I turn off In and now solve for V sub C of S. So let me take the circuit here, and I'm going to try to copy that down. So that's half the problem. Now I need to do the other half, which is to say, if I go back to the circuit, what happens if I now turn off the current source and look only at the voltage source? Okay, so here's the circuit again. So step 2 is to turn off In. Okay, So to do that, basically I just remove that part of the circuit. Okay. And I guess what I'm going to do is, instead of calling this V sub C of S, I'm going to call this V sub C V in. Okay, like that. All right. All right. Now to do this problem, I got a couple of different approaches. What I like to do with this one though is what I'm going to do is I'm going to say I have if I cut the circuit right here where I made that dashed line, if I cut the circuit right there, everything to the right of that could be replaced by a Thevenin equivalent circuit. In other words, here's R1, here's R2, here's Vn of S. That can be replaced by an equivalent circuit. I don't know what I'll call this. I'll call this V1 of S. Okay. Well, I can say that V1 of S, the open circuit voltage here, would be R1 over R1 plus R2 times Vn of S. Okay. That's how I get the open circuit voltage. So in other words, I'm replacing this network with some network that looks like this, where this is now my V1 of S. Okay. And I'm saying, what is this impedance here? Well, that impedance would be the impedance that a current flowing into these terminals would flow through. So a current here would go through the parallel combination of R1 and R2. So this is R1 in parallel with R2. So this whole network here becomes V sub C Vn of S. So that's across the capacitor. This is R1 in parallel with R2. And then I have V1 of S like that. Okay, this is SL. Okay, all right, and this is 1 over SC. So to do this, I've got a voltage divider now. I can say that V sub C of Vn of S equals simply on top 1 over SC over the series combination 1 over SC plus SL plus R1 in parallel with R2, which I'm going to write as R1 R2 over R1 plus R2 times V1 of S. So I'm going to write that just simply as V1 of S for now. Okay. Now again, I got to simplify that guy. So what do? I multiply top and bottom by, in this case, at least SC. So I have 1 over SC. Let me rewrite the expression here. I'm going to move my V1 of S over here. Okay. 1 over SC over 1 over SC plus SL plus R1 R2 over R1 R2. Okay. And then multiply this by SC times R1 plus R2. SC times R1 plus R2, like that. And what do when I make that multiplication? Well, SC times SC becomes 1. So on top, I get R1 plus R2. On the bottom, I'm going to get R1 plus R2 plus S squared LC R1 plus R2 plus SC R1 R2. Okay, so to simplify this, one thing I need to remember is that V1 of S is a function here. All right, and so I got to make a replacement. So I got to say this whole thing becomes R1 plus R2 over R1 plus R2 plus S squared LC times R1 plus R2, like that. All right, plus R1 R2 times SC, all of that times R1 over R1 plus R2 times Vn of S. And that's simply by substituting my result for V1 of S from above. Okay? So then my final transfer function becomes Vc Vin of S over Vin of S. Okay? That's equal to this guy, R1 plus R2 over R1 plus R2 plus S squared LC times R1 plus R2 plus SC R1 R2 all times R1 over R1 plus R2. So if I plug in some numbers to that guy, what do I get for that? Well, on the top, I'm going to get 18 over 18 S squared plus 45 S plus 18, okay? And then here, so what do I have? I have times 3 over 18 for R1 over R1 plus R2, okay? All right, so if I wanted to get the final result, what I have right now is that V sub C of S would be equal to V sub C Vn of S over Vn of S. That's the transfer function from Vn. All of that times Vn of S plus V sub C In of S over In of S, all times In of S. Okay, so I could use this expression right now to find the result for the total voltage if I wanted to. All right, we're not going to go any further. I just wanted to do that analysis in an example here. Okay.